Welcome to practice number 103, and today we're talking about making non-pneumatic tires quieter. So first of all, there's aeroacoustics and there's non-pneumatic tires, which a lot of people are not aware of because considering that they are quite new. So let's talk about these different aspects. So we're going to look at a paper called Numerical Investigation of Aerodynamic Noise Reduction of Non-Pneumatic Tires using non-smooth riblet surfaces. And this is an open access paper, so you can find it in the link in the description. And in podcast number 101 and 102, we looked at riblets, so if you listen to that, you should have a good understanding as to what these things are. And it's quite surprising that there are even more uses for them. So in this particular case, noise reduction. So we'll talk about how riblets potentially reduce the noise of just things in general, and in particular this non-pneumatic tire. So first of all, let's talk about what non-pneumatic tires are. So they're tires that are used on cars, but instead of having the typical like rubber tubing that you blow up and then there's air that you ride along. It's all like just material which doesn't really deform very much. It's all solid. It's quite a rigid design. So I have a picture here in Figure 1. If you're listening to this on Spotify, you can see the video on YouTube, and there should be video on Spotify as well. And you can find the link to the YouTube in the description. So the picture here shows two cylinders effectively. So you have a middle cylinder, which is the rim on like a regular car, imagine that, the hub. And then you have another cylinder over the top, which is of a greater diameter. And then there are these spokes. So all these lines that are going from the hub, from the inner cylinder to the outer cylinder. And this provides the stability. So think of like a bicycle tire, for example, bicycle wheel, for example, where you have all these spokes going from the outer rim to the inside axis bit, but just make that axis much bigger. And then you have the non-pneumatic tire. So in this particular case, the hub is actually quite large. It has a diameter of 400 millimeters, 410, and the outer, like the actual tire bit that you'd sort of assume to be the tire, the outside cylinder, has a diameter of 593 millimeters. So the spokes are not very large at all. They're actually only less than 100 millimeters long, and they're just spaced all around the inner hub. So that's what a non-pneumatic tire is. Also, we should mention that they don't really deform very much. So one major difference between this type of tire and a pneumatic tire, is that a pneumatic tire has a contact patch which is quite large, relatively speaking. It's actually very small considering how large the vehicle is, but compared to this, it's even smaller. So the contact patch of a regular car for a regular tire is about the size of your hand. That's it. So your car is pretty much touching the ground with only 4 hands. That's less than some people's feet, effectively. Like some people's feet are more than 4 hand areas with shoes on. So with these tires, though, these non-pneumatic tires, the contact patch where the tire meets the ground is very small. And this is because the tire doesn't really deform very much. And we'll get into the contact patches a little bit later as well. Let's start with the rest of this paper now. So they say, since pneumatic tire inventions in 1888 by Dunlop, it has been the primary choice for use in cars. But this comes with several drawbacks, including susceptibility to catastrophic damage, complex manufacturing processes, and air leakage during driving, and its required air pressure limits to free the design space of a car. Unlike a conventional tire, the non-pneumatic tire, the need for a tire to be inflated with air to support vehicle weight is eliminated since the spokes or hubs are used. This has several advantages, including a low rolling energy loss with the use of low viscoelastic energy loss material, low mass, and low contact pressure. So in other words, a vehicle, when it's driving along, there are really 2 major parts of energy loss. The first is drag, the second is rolling resistance. So there's a typical rule of thumb where if you're going below 70 kilometers per hour, so like 40, 45 miles per hour, the majority of the energy loss of a vehicle, like your regular car, comes through rolling resistance. When you go above 70 k's per hour, then the drag becomes the dominant energy loss mechanism. So below 70 kilometers per hour, which is pretty much most people's driving situations, the rolling resistance is the most lossy. So having a non-pneumatic tire, the rolling resistance drops, is what they're saying here, which is very good. So non-pneumatic tires adopt a spoke and tread structure composite of a polyurethane material. The geometric structure and material performance parameters have great influences on rolling resistance, vertical stiffness, and contact pressure of the wheel. Under the same load, the contact footprint of a non-pneumatic tyre is rectangular. On the other hand, it's oval for pneumatic tyres. Moreover, non-pneumatic tyres do not depend on air to support the weight of the vehicle, and the flexible spokes result in high tyre elasticity. So the spokes are not that flexible. They're obviously more flexible than a typical rim, like the spokes on a rim of a regular wheel on a car, but they're not still like really flexible. They just have a little bit of flex in them, which everything deforms with force. In addition, non-pneumatic tyres boast anti-barding and explosion-resistant characteristics and offer excellent driving safety. So explosion resistance is quite good. I like to have my tyres to be immune to explosions. In fact, I have a torch as well that's explosion resistant, so it's good to go hand in hand. So the spokes of non-pneumatic tyres are generally arranged circumferentially. So in other words, you just have the hub and then the spokes are going from the hub all the way directly out to the rest of the tyre, and they go around the hub. The width of the spokes is equal to the lateral width of the tyre, so the width of the tyre is the same width as the spokes. When the rolling speed is high, the spokes cut the air speedily, resulting in a complex airflow and generating a loud aerodynamic noise. So that's one major problem, because you have all these spokes, you now have all these things just cutting through the air, which is not only going to result in more drag potentially, but also more noise, because you have more surfaces creating a lot of unsteadiness, which is where noise typically comes from. Their results, some people investigated some non-pneumatic tyres, and their results showed that an open structure always results in a more complicated flow field distribution compared with that of a conventional pneumatic tyre. And that makes sense, because a conventional pneumatic tyre, you pretty much only have the tyre itself, which is a solid, and then you have the hub, and then you have the spokes. And the spokes are really the only part where the air can get through and be chopped up a little bit. And then you have the brake disc inside, which blocks off some of that potential problem there. So the reason why the non-pneumatic tyre results in a more complicated flow field, they say, this may be one reason for the limited application of the non-pneumatic tyre in vehicle tyre design. In other words, this is potentially one limitation as to why they haven't been used to date. The aerodynamic noise of non-pneumatic tyres have become a key challenge in clean energy car research. However, relatively few reports have discussed aerodynamic noise reduction methods for this type of tyre. Because aerodynamic noise originates from fluid motion, controlling the method of flow to alter the aerodynamic noise generation is now a generally accepted strategy. So in other words, trying to control not only the drag of a vehicle and the lift and side forces, etc., but also the aeroacoustics of vehicles is very common. In fact, there's it started probably with Rolls-Royce. There was an ad with Rolls-Royce back in the 80s or so, and it said like something along the lines of Rolls-Royces are so great or whatever, that the most annoying thing about driving Rolls-Royce is the small hum of the outside noise or whatever. So that's how important noise has become. It started off with them, and it's becoming more and more important with other vehicles. For example, in a lot of, I think, Toyotas and Hondas, around the for the radio, the antenna coming out, they have a wire wrapped around it to reduce the noise coming from that, because that is a cylinder, and that results in a vortex shedding frequency, and that results in tonal noise. So to reduce that little bit of noise, putting a little bit of wire around it helps break up that coherent shedding. So that's the reason why noise is important. So boundary layer control utilizing riblets with different cross sections has received considerable attention. And in podcast number 101 and 102, we looked at that as well. And then some other researchers confirmed that a trailing edge riblet structure can effectively reduce the trailing edge noise of a wind turbine blade after obtaining a total sound pressure reduction of 3 decibels. So for sound pressure levels, we measure them in decibels. A 3 decibel reduction means that you're cutting the sound in half, which means it's half as loud. Now, another interesting fact that I learned the other day, and just as a side bit, is that if you have a sound pressure reduction of 6 decibels, that is the equivalent of doubling the distance you are away from the sound emitting source. So the further you get away from a sound emitting source, the quieter it becomes. Obviously, the noise attenuates. But so let's say you're 10 meters away from the source and the decibel level is 90. Then you go 20 meters, double the distance, the sound pressure level will be 84 decibels now, so 6 decibel reduction. So that's a cool little rule of thumb for you. Inspired by the awareness that the riblet structure can reduce aerodynamic noise, these researchers propose a bionic method wherein the riblet structure is arranged on the spoke surface of the non-pneumatic tyre as one of the flow control methods to reduce the aerodynamic noise. First, a three-dimensional geometry of the non-pneumatic tyre is established, and its surface pressure coefficients at 80 km per hour are presented using computational fluid dynamics. A comparison with published test results is used to validate this model. Then, going from there, once it's validated, they're using an unsteady flow based on large eddy simulation, so LES, and the aerodynamic noise equation of the Fox-Williams-Hawkins equation, which is a very common way of calculating noise, is chosen to predict the sound pressure level, while the distribution, pressure, and strength of the acoustic sources of the tyre are identified using vortex theory. Now, this is a cool theory that we're going to get into a little bit later, and we haven't covered it yet on this podcast, so I'm looking forward to that. Third, the next step is a non-smooth riblet surface is established on the flexible spokes based on the fluid boundary layer theory, and the effect of the riblet structure, param size, position, and direction on the sound pressure level is analyzed. So in other words, they're going to be looking at putting all these riblets on these different spokes and seeing the effects of these things on the aeroacoustics. Finally, they're going to look at a comparison of the fluid field parameters using the vortex theory to investigate the noise reduction mechanisms. If there are any noise reduction mechanisms, I'm not going to tell you whether there are or not. We'll leave it to later. So in table 1, they actually have the dimensional parameters of the non-pneumatic tyres, and just a few things that I wanted to point out. First of all, the width is 195 millimeters, which is quite thin. Like most tyres are significantly greater than that. Most tyres are above 200 millimeters, so being below that's fairly thin. There are some cars that do have such thin tyres. For example, the BMW i3. The number of spokes here is 50, so that's a lot. Most cars have like 5, 7. 50 is a lot, and the spoke thickness is only 4.2 millimeters, so they are very thin. But there are a lot of them. That's why you can have such a lot of weight on them. For example, a bicycle wheel, the spokes are very thin as well, but because there are so many of them, you can take a lot of weight. So, moving on to the CFD model, because the non-pneumatic tires, the model is symmetric along the center plane. So in other words, in the direction of free stream, the left side is symmetrical to the right side. Only half of the model is used for this calculation. The CFD model and domain sizes are shown in figure 2. So let's look at figure 2 here. So they have a regular rectangular domain. It's actually like a rectangular prism. And down the middle of it, they've cut it in half and put that as the symmetry plane. So you're only simulating one side of the tire, or not one side of the wheel, sorry. So is this a good thing to do in this particular case? Let's think about it. So the flow physics from a wheel is fairly complicated. This is good in terms of it's only a single wheel. It's not attached to a car. If it were attached to a car, you wouldn't be able to do this because the left side of the wheel is affected differently by the car to the right side. But because this is just an isolated wheel, the flow physics does get simplified a little bit. So with this typical wheel, you're going to be getting vortices around the base where the wheel meets the surface. You're going to get vortices around the middle section, so the shoulders. That's the technical term for them, the shoulders. Then you're going to get a vortex, like this horseshoe vortex, on the top. So these are steady vortices that are being formed. Along with this, you're going to be getting some unsteadiness. However, typically with isolated tires, this unsteadiness is a secondary factor. These steady vortices that always produce the vortices around the base, which are called jetting vortices, the ones around the shoulders, and then the ones around the top, they're all like dominating the flow here. So in this particular case, it is okay to use the symmetry plane because the left side should be symmetrical to the right side, and there's not really a periodic shedding from one side to the other, this fluctuation. So that should be okay to get like a 90% accurate result, in other words. So that's fine. So some researchers found that close to a tire, the geometric shape of the tire road contact simply affects the aerodynamic characteristics. And this is an understatement, Ali. I mean, there are hundreds of researchers that have found this. And the reason why is because, as I mentioned earlier, just a few seconds ago, where the tire meets the road, you're going to be getting a contact patch. And this contact patch results in a lot of the fluid not being able to travel underneath the tire, obviously. And this has to then result in this roll up around the sides of the tire, around the base, into the jetting vortices, one on one side, one on the other. And this is a major problem for aerodynamics of cars, and it adds a lot of drag to the car. And trying to get rid of this is a major problem. One caveat to this is that when you have a tire with longitudinal grooves, so these are grooves that go around the tire circumferentially, at the contact patch, there is still an opening between the front and the back, because these little longitudinal grooves are little passages that the air can go through. So that allows some of the fluid to reach the back still, and so some of the fluid doesn't go into the jetting vortex in real life. But if you simplify a tire to the point where it's just a smooth surface, or when you have like F1 cars, for example, they don't have tread, they do have a much, this exacerbates the jetting vortex because they have a lot more fluid having to be jetted out the side to get away from the front of the tire and move downstream. So the tire contact patch does make a massive difference to the aerodynamics. So when a vertical load of 3,000 newtons is applied to this tire, there will be a platform deformation in the contact patch. In order to reflect the platform deformation, a block is used at the contact angle to indicate the contact shape. So in other words, in figure 4, they have their mesh set up. They have the tire touching the ground. Because you have a loading on it, there is a little bit of deformation here. It's not as much as a regular tire, but there is still a little bit. And they're then just simulating this is what they're saying. So according to the contact length of the tire obtained from Abacus Simulations, which is another software for this is FEA, I'm quite certain. The length of the flat block is 16 millimeters, so it's not very much at all, like half an inch. This is a lot less than a typical tire. So what that means is also that you're going to have a much greater pressure in the contact patch than a regular tire as well. So let's talk about the boundary conditions that they've used for this CFD. So the boundary conditions are set as follows. The inlet velocity is 22.22222222 recurring meters per second, which is 80 kilometers per hour. And it's going in the the X direction, so that's free stream. And when you calculate the Reynolds number based on the tire diameter, that gives you a Reynolds number of 91,000. Oh, sorry, 900,000. So that's very high. It's pretty much turbulent. So a symmetry condition, as we mentioned, is placed around the middle, or like slicing through the middle of the tire, so left side to right side. The ground is treated as a non-slip wall with constant moving speed along the positive X direction to match the free stream velocity. And non-slip means that the boundary layer will form. And then we have the pneumatic tire. The non-pneumatic tire surface is taken as a non-slip wall with an angular velocity of 75 radians per second. And this corresponds to the translational speed of the road. And the remaining surfaces are set to zero pressure conditions. So one interesting thing we should talk about here is one of the most common two-equation Reynolds average Navier-Stokes models. So one of the most common turbulence models that you use in RANS simulations is the realizable K-epsilon model. So this is a very particular type of model which you can only use in certain conditions. And these conditions actually do suit it because it's very turbulent. When you go to more laminar or more transitional flows, then the K-epsilon is not very good at all. In fact, even in this particular case, I have investigated this as well, and using a better turbulence model such as the KME SST is actually better in this particular case as well for automotive. But K-epsilon is okay in terms of computational power versus accuracy. If you want to get very accurate, then you go to a much better turbulence model, or even go to DES and LES, which jumps up the computational power a lot more, or the resources, sorry. So in table 2, they have all these different grids that they've meshed this CFD with. So they're doing a grid independency study, which is good. That's what you should always do. Now, the way that they've done this is that they've changed the maximum cell size, they've changed the first layer boundary thickness size, and they've changed the number of boundary layers. Now, they've changed this all together with different grids. So we go from grid 2 to grid 3. Not only does the maximum the cell size change, so does the first layer boundary layer thickness change, as does the number of boundary layers that the inflation layers that you have. So is this a good way of doing it? It's okay. I mean, it's not completely thorough, because if you were to do a super thorough CFD analysis, you would change each one of them sequentially, but then that would take a lot of resources. Doing it this way is quite unlikely that you're going to be getting 2 different grids that are very different but still produce the same results and not being grid independent. So this is okay. You can do it and you will get fine results pretty much all the time. So for the coarsest grid, they have a total of 2.2 million cells. For the most refined grid, they have 11.7 million cells. So a lot here. And they say the converged results of the let's talk about the results of this mesh independent study. Figure 5, they have the distribution of the pressure coefficient around the tire. So let me explain what's happening here. They specify the 0 degree angle of attack, 0 degree, sorry, as like the very front of the tire, so it's 90 degrees from the road. And as you go around, you loop the tire in 360 degrees, and you go to the contact patch first. So the contact patch is 90 degrees, then the back of the tire is 180, the top of the tire is 270, and then the front again goes to 0 or 360. That's the convention here. And what they found was very normal. So first of all, the pressure coefficient is always very high at the front of the tire because you have all this air coming crashing in and you have a lot of stagnation pressure. As you get to the contact patch, the pressure is still very high because you have the stagnation there. But then once you pass the contact patch, you get a very low pressure, and that's because now you have almost no air getting around there, and then it has to recoup. So, and then from there, you start to get an increase in pressure as you go back around the tire. So there's this discontinuity between the front of the contact patch and the back of the contact patch because of that no air getting through. As I mentioned, in real life, you have the longitudinal grooves on regular cars, and that means that this discontinuity is actually not as discontinuous. In fact, often there is no discontinuity. There's like a drop, but it's not a discontinuity. It's still continuous to some extent. So what they found with these grids is that grids 2, 3, and 4 match pretty well. Grid 1 is not very good. There's some deviation when you get to the back of the wheel, and that's to be expected because now you have a lot more complex flow physics of the jetting vortices coming around, plus all this air rushing in that you have to mimic, and that's very difficult to do. But grids 2, 3, and 4 are quite good. They've found that grid 3 and 4, there is almost no deviation between the two, so they're going to be looking at just using grid 3 here, because grid 4 is an overkill. So they have the grid 3 from the grid independent study is good. They're moving forward with that, and now they're going to be comparing this grid 3 results with real life data. They get it from a bunch of different sources. They have 2 which are from pneumatic tires and 1 from a non-pneumatic tire. And to the best of my knowledge, these are all experimental data. So first of all, they all follow the same sort of trend, which is nice. But the pneumatic tires obviously follow a slightly different trend to the non-pneumatic tires. There are also just some bumps along the way which don't agree with each other. However, the thing to note in this is that the CFD that they've done here for grid 3, which is the not the finest but quite fine, matches very nicely with the experimental data from literature for non-pneumatic tire, the pressure coefficient distribution. So in other words, they've now validated their CFD with experiments here, which is good. So they've not only done a grid independence, which you should do, but also a mesh validation process as well, which is good as well. So let's move on from here. Let's talk about the aerodynamic noise simulation. So the convergent results of the steady calculation, which was what we were just talking about, is used as the original flow field, and the LES method is used for the unsteady calculation. So in other words, they've used this steady state just to validate their general process for aerodynamics. And now they're going one step further and using this as the initialization process for the LES model. A couple of benefits of this is, one, you're going to be getting a much easier way, like a easier starting point to get your LES started, because sometimes if you start your simulation, you can get it diverging before you get it converging. So that can present problems. So using a better starting point, having a steady state simulation to work from, is much better there. Also, you're going to get it to converge much quicker because a lot of the legwork has been done by the steady state simulation that you don't have to do with this more computationally expensive LES approach. So they say, first, the time step is set to 1 by 10 to the minus 3 seconds, and is iterated for 2,000 time steps. The total computational time is 2 seconds then, meaning that the total time is 5 times that of the domain for airflow. So in other words, the airflow goes through the entire domain 5 times by the time this initialization process has ended. After this 2,000 step process, the flow field tends to be relatively stable. Next, the time step is reduced to 2.5 by 10 to the negative 5 seconds. That's very low. And the unsteady flow field is recalculated with another 2,001 steps. At the same time, The acoustics model is now opened, so it's now allowed to proceed. So we can calculate the acoustics. According to the Nyquist sampling theorem, where it means that they can measure up to 20,000 kilohertz sound. So in other words, Nyquist sampling theorem says that the maximum frequency of sound that you can accurately measure is half that of your sampling frequency. And the reason why is because if you have sampling frequency is less than that, you start not being able to resolve the wave properly. So that's why you have a limit here of 20,000 kilohertz, which is still quite high. That's pretty much the limit of human hearing anyway. So the sound pressure level is used to evaluate the aerodynamic noise level in decibels, calculated as the sound pressure level is 20 times the log of PE divided by Pref. So PE is the effective pressure at wherever you're measuring it, and the reference pressure is usually set to 2 by 10 to negative 5 pascals, and this is very standard. So one thing that should be noted here, it also depends on where you're standing. So I think the international standard is you have to be 1 meter away from the source, and then you take the measurement. But it depends on just how you define it, really. So moving on, we get to an equation, and the reason why I want to talk about this is because it sheds a lot of light onto aeroacoustics. So equation 7 can be considered, can be used to consider the interaction between the mean flow and the wave propagation. And equation 7 can be considered as an appropriate convective vortex sound equation. The left side of equation 7 describes the propagation of sound waves in a non-uniform flow. The right side of the equation represents a vortex source. For isentropic low-speed flows, the divergence of the Coriolis acceleration experienced by the fluid is a basic factor that causes the flow to occur. It means physically that the sound produced by the tensile deformation of the vortex is the velocity field. So in other words, what all this means is that this equation here, which consists of partial differentials of velocities and pressures, and then the density times the divergence of the vorticity cross product with the velocity. If you want to know this equation, just look at the paper. It's quite difficult to explain in words, but you just have a bunch of properties of the fluid that you're manipulating to relate some straining with vortex straining. So what this means is that the aerodynamic noise is derived from the stretching and rupturing of a vortex. For a steady and flawless flow, the total enthalpy is constant. This means that there is no sound generated during this flow. It can be seen that the vortex theory, then, this theory, relates the airflow radiation to the magnitude of, the airflow noise to the magnitude of the vortices. So in other words, the noise comes from vortices, is what they're saying, and the rupturing and stretching and pulling of these vortices, and also the creation of these vortices. So that's why I wanted to cover this equation, because it now relates sound back to vortex production and breakdowns. So one thing that is also important to talk about is something called the Lamb vector, and I want to talk about this briefly. So the right side of this equation 7 can be defined as the Lamb vector. The Lamb vector is the divergence of the cross product of the vorticity and the velocity vectors. So Lamb is actually relates to this old fluid mechanist called Horace Lamb, and he's probably the most influential fluid mechanist of all time, who no one has ever heard of. And you may not have heard of him, and if you haven't, check him out, because he lived back in the early 1900s and late 1800s. And the only reason why I know about him is because at the university that I did some of my study at, they had a building named after him, which no one knew who he was either back then, but because I was doing fluid mechanics, I learned. And almost no one's heard of him, and he's had such an important impact on fluid mechanics. So that's why I just wanted to cover that here. So, as I mentioned earlier, where you take the sound reading determine impacts what the sound pressure level is. In this particular CFD, they have 5 different points that they're taking sound pressure measurements from, and they're measured all in a 1 meter radius around the tyre, but they're measured equiangular around the tyre from 0 degrees to 180, and because they're only simulating half this tyre, they can just assume that the other side is the same in the symmetry plane. So let's talk about the effects of the non-smooth riblet structure on the noise propagation. Oh, sorry, I should cover actually the sound being produced. So they found that for just the regular tyre, at different points. So when you're directly upstream of this tire, the sound pressure level is 63 decibels. The lowest occurs when you're just behind, like let's say you have the tire which is at 12 o'clock, then you're going to about 7:30 to 7:30 maybe, and that is where the noise is lowest, and that's a decibel level of 59. However, the total sound pressure level is 71 decibels for this tire. The worst situation is directly behind the tire. You get a sound pressure level of 69 decibels, and then the rest of the tire is between 60 and 63 decibels. So that's the tire without any riblets. Let's talk about the effect of non-smooth riblet structures on the non-pneumatic tire aerodynamic noise. So, because the spokes are the primary source of noise, to reflect the non-smoothness of living creatures, so sharks, a series of parallel non-smooth riblet structures are placed on the surface of the spokes. To prevent damage to the spoke structure, convex rather than concave riblets are preferred. So in other words, instead of like chiseling straight into the spokes to create these riblets, they're actually just sticking on these triangular structures on the outside to ensure that you still have the structural stability of the tire, but you still get the riblets. So, because noise reduction by non-smooth surfaces affect the flow motion in the boundary layer, the dimensions of the riblet structures are set below the flow boundary layer thickness. Now, I didn't really understand this point too much because, and I'll explain why. So what they're saying here is that they want to make the riblets as small as possible, so they're making them like less than the boundary layer thickness. But the thing is, on sharks, which is where this comes from, they're that small anyway, like they're really small. They're in like the viscous boundary layer, and they still have a massive effect on the flow. So it's not, I don't really understand what they mean here. They will still have an effect on the flow having them this small. Anyway, they talk about the riblets now. So in figure 10, they have 8 designs for these riblets. They have schemes A to D are basic schemes, and E to H are different combinations of the 4 basic schemes. So case A is effectively riblets going from left to right through the spoke. Case B is going vertically. Then case C and D are when you have them on the actual hub and the tire, not actually the spokes. Then case E and F, and G and H, they have just like all crisscrossing riblets going around. It's a little bit difficult to explain these configurations in words. So if you want to look at the paper, you can see them here. So let's talk about the influence of positions and directions of the riblet structures on the aerodynamic noise. Similar to rotating machinery, the rotation of a non-pneumatic tire means the rotation of the airflow within these cavities simultaneously, and the spokes cut the air. With this complexity, the position and the direction of the riblets may influence the air motion, resulting in different sound pressure levels. So, to explore a reasonable riblet structure, it is assumed that the cross-section of the one riblet is equal to an equilateral triangle with a side length of 3 millimeters. This is different to the riblets we're looking in podcast number 101 and 102, where we had riblets of isosceles triangles, and their angle was, I think, 59.13 degrees from memory. It's like 59 or so. But these riblets here are equilateral, so that means that they have a height of 3 millimeters and they have the angles of 60 degrees, I think. So the spacing between these, between 2 adjacent riblet units, is twice the side length, as shown in figure 9. So let's look at figure 9 here. And sure enough, they have a figure here with the riblets. They just imagine a bar with all these points coming out of it, and they're in triangles. The distance between 2 triangles is 2 times the distance of one riblet length, and they have an angle of 60 degrees. So the riblet structures can be placed on the front and the rear surfaces of the spokes. The arrangement may be radial, circumferential, or lateral, or on either surface. So in figure 6, they show the changes in the sound pressure level with various riblet structures. They say the variance between the two, so between the non-riblet case and each riblet case, is shown here, and they find that some of them increase the sound pressure level a lot. So some of them increase it up to 5 decibels, which is like more than double. It's almost quadruple, like it's about 3 times the amount. Some of them reduce it by 5.2 decibels, which is a lot. That's case B. And case B is where you have the spokes and the riblets running radially. So they go from the hub to the wheel, to the tire, sorry. Then you have, let's look at case A. Case A has a reduction of 3 decibels approximately, which is a riblets going on the spokes, but they go from left to right, so crisscrossing along. But either way, they still both have a good reduction. Case C, which is where you have riblets on the hub and the tyre, the inside of the tyre, you actually get the increase of 5 decibels, so that's really bad. And in case D, where you have riblets in the same locations but going a different direction, you get a reduction of 1 decibel. In this particular case, 1 decibel probably would be within the error, so I wouldn't assume there to be too much of a difference here potentially. But the largest reduction is 5.1 decibels, which is a lot. Even getting like 2 decibels is something to really write home about, so having 5 decibels is fantastic. So in table 7, they have the changes in the sound pressure level with the riblet dimensions. So now they've been looking at the different effects of different riblet structures, and they have them ranging from a 1 millimeter height to 5 millimeter heights. And the reason why they went to 5 millimeters is because the spoke thickness itself has 4.6 millimeters, so they don't want to get too big, otherwise you may start running into other problems there. The addition of an oversized convex structure can significantly affect tire structures and cause deformation under the loading. So that's why they didn't go any higher either. So the differences between the total sound pressure levels of the 5 schemes are compared with the original model. As seen in table 7, the size of the riblet structure considerably affects the aerodynamic noise. A riblet structure with a side length of 3 to 4 millimeters can effectively reduce aerodynamic noise. This result proves the feasibility of using riblets on non-smooth surface structures with appropriate parameters to effectively reduce the aerodynamic noise. However, the side lengths that are too long or too short diminish the noise reduction effects and can even increase the noise level. So let's look at this. When we had a very small height, so 1 millimeter, the sound pressure level actually jumped by 3.5 decibels for some reason. They didn't go into the flow physics here, but there's some funky thing going on here. When you have a height of 5 millimeters, the sound pressure level increased by about 0.5 decibels, which is probably within the error. When you have heights of 3 millimeters and 4 millimeters, the sound pressure levels are minus 5 decibels, so they're much lower. It's a bit strange, the fact that at 4 millimeter heights, you get a sound pressure level reduction of 5 decibels. When you go 1 millimeter height, only 5 millimeters, you all of a sudden have a 0.5 decibel increase. So it's a 5.5 decibel increase overall, like the difference between these two, just for a 1 millimeter change, even though going from 3 millimeters to 4 millimeters had almost no effect on the sound pressure level reduction. So there's potentially something going on here which has changed the flow physics dramatically. Maybe it comes back to that boundary layer thing I was talking about earlier. However, the fact that the 1 millimeter height riblets seem to have a negative effect as well indicates that maybe there's something else going on as well. I'm not too sure. And further studies would be beneficial. So in figure 11, the noise reduction level of scheme B3, which was the greatest, is shown. And this is when the heights were 3 millimeters. And it shows the noise spectrum compared to the original non-pneumatic tyre, so the smooth non-pneumatic tyre. The overall spectrum trends for the two models are the same. So they have approximately the same like wiggling going along with different frequencies. The sound pressure level gradually decreases as the frequency increases for the riblet case, but at most frequencies, the sound pressure level of this 3 millimeter height riblet is lower than that of the original model. The reductions are greatest in the frequency bands of 20 Hz to 600 Hz and 2000 Hz to 3500 Hz. Apart from that, there's very little difference between them. So these are the two regions where this reduction occurs. So let's talk about the noise reduction mechanism of the non-smooth riblet structure. In figure 13, we have the comparison of the Lamb vectors of the original non-pneumatic tyre and the modified tyre with the B3 riblets, so the 3 millimeter height riblets. So the Lamb vector, as we mentioned earlier, is a key indicator determining where noise comes from in this particular case. It is the divergence of the vorticity cross product with the velocity vectors. When you see a lot of red, it means that you're getting a lot of sound effectively coming from these regions. So the figure 13 reveals that the extreme values of the Lamb vector are concentrated at the openings of the discontinuous spoke cavity. So in other words, between each spoke is where you're getting a lot of noise coming from. This means that the flow vortex is mainly generated near these openings, and all openings are aerodynamic noise sources, which is to be expected. I mean, you have all these just like the spokes just chopping through the air, creating a lot of vorticity and a lot of unsteadiness, you're going to be getting a lot of noise. The non-smooth riblet structure plays an important role in weakening the vortex flow. The riblet surface breaks the large vortices of the spoke cavity into smaller vortices, thereby suppressing the fluid vortices produced and ultimately reducing the aerodynamic noise of the non-pneumatic tire. This is interesting because if we come back to the graph showing the frequency versus the sound pressure level, as we mentioned earlier, that a lot of the frequencies, the 3mm riblets have reduced the sound pressure level a little bit. It's just a broadband reduction almost. There are some regions where there's similarities, other regions where there's reductions. One reason why there's these reductions in these particular areas is because, as they mentioned, the riblets are now breaking up these large vortices into smaller vortices, and smaller vortices typically have smaller sound, less sound to begin with, but also they can't really coalesce very easily into being larger noise producing vortices. So that's potentially why we're getting reductions here. So, in conclusion, inherently, the flexible spokes are the main aerodynamic noise source for these non-pneumatic tires. In order to control the flow and reduce the aerodynamic noise, a bionic non-smooth riblet surface structure is arranged on the spokes of the non-pneumatic tires. They come from sharks, these riblets. The influence of the position, direction, and the size of the riblet structures on aerodynamic noise was analyzed, and it is evident that by appropriating the exact parameters that they like certain parameters, you can reduce the noise by 5.19 decibels. That's a lot. From the perspective of vortex theory, which was when we were talking about how vortices produce noise and how they do that through that mathematical equation, the mechanism of reducing noise is that the non-smooth riblet structures significantly decrease the Lamb vector near the spokes and break the band-like distribution of the Lamb vector at the spoke edges and thus the aerodynamic noise of the non-pneumatic tire. In other words, the riblets break down these vortices into smaller vortices, which reduce the Lamb vector, which is the mathematical representation of the noise. However, the effects of the deformation of the non-pneumatic tire spokes, the wheel eyebrow, vehicle structures, and other structures on the aerodynamic noise source of the tire are not considered. So in other words, this is just a tire in isolation. So the results, they will be fairly applicable, but not 100% applicable, just the general mechanism. In addition, the riblet size parameters given herein may not be optimal. These issues provide avenues for further future research. So that's in this podcast. I hope you enjoyed it. And if you know any other studies on this, I'd be interested in knowing that because it's a cool topic. And if you want to get better at CFD yourself, we're talking about CFD here, check out our links in the description below. There are courses that you can do to get better, or you can take courses in the links description which have theory involved, so you can learn theory and become better at that as well. And if you're doing CFD and you want to validate your model, if you don't validate your model, then you can't really trust it. And you do that through having real life data. Either that's through experiments or you go out into the real world and you take your measurements. Now, in both of these situations, the density of air does change every day, and it changes from hour to hour. So if you take your measurements and the density of air is 1.18 kilograms per meter cube, for example, you come back to your computer and you do your CFD. You didn't know what the density was, so you just say 1.2 kilograms per meter cubed. Well, your experimental data that you're using to validate your CFD is now different because the density of air is different that you used. To get rid of that error, we made the atmosphere hawk, which actually measures the density of air for you, and it gets rid of that error, which is about 2 to 4% usually on a regular day, and even more between weeks and months and seasons. It can be up to like 15% sometimes, depending on differences. And so that means you're getting a lot of errors that make validating CFD much harder. And it means that your model will never be validated truly, which means you can't trust it. What's more, it just makes your experimental data more accurate as well, which is what you want when you want to publish papers. So pick one of them up in the link description, the Atmosphere Hawk. It's an instrument we make for you to make your experiments better and your CFD better. And I'll see you next podcast. Peace out, amigos.